it okay if I record the session? Is everyone okay with that?
Okay.
Okay, thank you.
Yeah.
So the plan for today is to understand how the convolution part of the convolution network works. How does it find patterns inside images? And so that's one aspect that we'll go through. And the second aspect that we'll go through is last time when we built a classifier, we used a loss function called cross entropy. So we'll understand what is entropy, what is cross entropy, and just to quickly share the key idea behind machine learning is in supervised machine learning is that you have some predictions which we would call labels. So let's say you're predicting dogs and cats. So the label for dog is 1, cat is 0. So you have all these images for cats and dogs with labels, and you're trying to make predictions. Let's say with probabilities. So you get 0.9 for a dog, or 0.1, which means it's more of a cat. You want to minimize the distance between what the label is and what your prediction is. And you need some way to measure that distance. So there are a lot of ways of measuring that. So cross entropy is a very popular one. For those of you who've used logistic regression, that uses cross entropy also. So we'll talk about these two things today. Does that sound okay?
Yep.
Awesome.
Yeah.
Avneet, can you minimize the Skype screen on your desktop?
Yeah. Okay. Can you guys see my screen in the Jupyter notebook?
Yes.
Yep.
Yes.
Awesome. So I have two notebooks for today. This is the CNN, and the other one is a cross entropy. So let's start with CNN first. So at some point in time, I'll also go deeper into neural networks. But essentially, a neural network is layers of neurons, where each neuron is sort of a function on the features. So convolutional network has certain convolutional layers. So if you're predicting, let's say, faces, then your first layer, if you can see at the left bottom, will sort of learn things like these. What are bright spots? What are dark spots? Combinations of those. So the first layers will learn some very simple things about images. And then if you look at the image on the right hand side, under faces. So as you go further in layers, these layers will learn things like, what do eyes look like? What do nose look like? what do ears look like? So it'll get slightly more sophisticated with its features. And if you look below that, that's an even later layer. That's learning more of what a face looks like and different kinds of faces. If you look at the right on cars at the top, you'll see similar idea. It'll learn what do tires look like, what does a door of a car look like, things like that. And the later layers, it's sort of learning what a whole car looks like. So there is a progression in the network. It'll start with very simple features like bright spots, dark spots, edges, circles, corners. Then, depending on what you're training it on, you'll start learning certain parts of those kind of images. So, like a nose or an ear or eyebrows for faces, and in case of cars, it's more the tires and the doors and wheels and stuff like that. Does that
Is that learning
sound?
natural, Avneet?
Sorry?
So I can see this as faces. It's being labeled as faces, correct?
Mm-hmm.
And then the model will figure out all different possible looks of a face, right? Including just the eyes and all that.
Mm-hmm.
But can it figure out that what it's looking at is an eye and a nose and a mouth versus a face? Unless we label it, how will it know that?
It does. So as we'll go through this example, it'll become a little bit more clear. But somehow the model is able to learn features by itself. So for a face, sorry, go ahead.
Without labeling, no?
It doesn't need the label that this is an ear and this is a nose. Let's say you're
know something different in the face.
Yeah, so let's say you're labeling male faces and female faces. Or if you're Facebook, you're giving the label of, let's say, your face and my face and somebody else, Shantanu's face. So those are the labels. And the model itself will learn what a nose looks like, and what are the different kinds of noses. And it'll try to learn that how your nose is different from mine and is different from Shantanu's. So you bring out a very, very critical point about deep learning, which is in deep learning, the models learn their own features. So in the past, we would have given it features, very specific, that would help it figure out these things. But with deep learning, it learns these features by itself. The cost, of course, is that the amount of images that you would need to give to train is very high, and the amount of training, the amount of compute power, so the iterations that it needs to be able to learn these features, those are very high. So that's a very important, very critical point, that in deep learning, the model itself learns these features. And as we go through today's pictures and slides, we'll get some intuition as to how it does that. That sound okay?
Yep. Go ahead, Ramesh.
Okay. So we're going to take a very simple example, and essentially what we are trying to do today is to get a basic intuition as to how the convolutionals, how these patterns work. So it's a very simple example, mainly to get an intuition behind what's going on. So it's an example of a black and white X. So we have an image which has pixels in it. Let's see how many. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 9 by 9 pixels. And they are either black or they're white. So can a CNN learn to say, okay, this is an X? And that's what we're going to see today. So the interesting thing, of course, is, as humans, when we see an X, like we see 4 of these, we look at them and we're like, okay, that's an X. But if you look at the first one, that's moved a little to the top in the corner. Second one has scaled smaller. The third one has rotated. The fourth one is thicker. So it's very easy for humans to figure this out, to look at unstructured data of images and sounds and language and make sense of it. Traditionally, for computers, it's very tough. Same thing we can see with the O. So how would a computer try to look at these two and say, is this an X or not? So the one right to us is an, seems like an X, but it's sort of distorted. So how would a computer figure that out? So one simple thing is look at places where both the images don't agree and the places where they agree. So here essentially black is represented in the matrix by a -1 and white is represented by a +1. So we are taking a very simple example to get the intuition behind it. So we are saying +1 show the X here, +1 show the X on the right hand side. And we look at the pixels where they disagree and the pixels where they agree. So that would be one way of computing similarity between images. And do you think that's really helping us much?
No, there might be other images that might agree.
Correct. So in this case,
different, no?
Sorry?
If smaller than the other, will that also make a difference?
If it's smaller than the other, yeah, that'll also definitely make a difference. Yeah.
Because match properly.
Correct.
So this image size also matters here.
Correct. So clearly this kind of similarity of approach, comparing pixels with pixels, is difficult. And as Sandal mentioned, size and other things can have an impact. So how do we sort of get around that? That was the big question. And the way that was resolved was to sort of break the image into smaller pieces. So instead of matching the whole thing, match certain patterns of one image with the other. So here on the left, we see there are three simple patterns. There is a right diagonal going down, there's a left diagonal going up, and in the center, this is more of an X. So these are sort of, what it's doing is it's looking at the fundamental aspects of his image and breaking them down. And then we'll see how it uses those to come to its decision. So you can see that what we see on the left, the right diagonal, we also find on the right. We can see a right diagonal, you can see a left diagonal, and we can see a cross. The relative positions have changed. So even if it is rotated, it's okay. If it's sort of thinner or thicker, it might still work. And we'll see how. So those kind of places, it can help. It may be smaller or bigger. Even then, these basic aspects should still somewhat match, not necessarily perfectly, but somewhat. So that's sort of the key idea behind CNNs, is find smaller features in images and use them to identify the larger picture. Does that sound reasonable?
Depends on the output of the.
The output is will come later.
Are you standardizing it, by the way? Will the small square?
Mm-hmm.
Would you say this much is a percentage of the total figure, or is it just a straight pixel level? One small pixel has these two lit up.
I don't understand. Can you please say that again?
No, are you maintaining the proportionality in these measurements? The matched pieces.
Maintaining proportionality meaning?
He's trying to ask how do you identify the smaller triangles, so the smaller squares. Is there a measure that says the smaller square has to be so much of the bigger image on its own?
That's a very good point. So that is sort of part of the architecture of the person who creates a model. That's a very good question. So every machine learning model will have some things known as hyperparameters. These are the things that the human building the model will try and figure out, and will change them and will play with them. So generally, a lot of times they'll take like 2x2s or 3x3s, as is the case here. But as the person building,
Would be 2x2 pixels.
In this case, yes, that's 2x2 pixels.
So in general, every image is broken up into smaller pieces and analyzed at that level.
It could be done at that level, or
2 pixels is too small, no? Okay.
You can take more pixels. It depends on the image size. So if you're the kinds of images that you're talking about, they're pretty huge, real life images. The kinds of images that they have in competitions like There's something known as MNIST computation, which has digits from 0 to 9. That'll have like 8 by 8 pixel images. So based on, so this is a hyperparameter, and based on your, sorry, go ahead.
The image size itself is 8 by 8. It's like one character.
The image size would be 8 by 8, so there are 64 pixels in there. And in that, you can have like a number written, handwritten digit.
So it's like an OCR thing. You're trying to recognize what the character is.
In MNIST, yeah. So they'll give you 60,000 training images and 10,000 to test. And those are handwritten images, as you said. It's up to OCR. And you train CNNs to learn that. So in that case, you can go with these small matrices of 2 by 2s and 3 by 3s. If you have thousands of pixels, then you can either increase them, or you can, there are ways used in CNNs that shrink the image to a smaller size without losing the important values. So then once you have shrinked it down, then you can use smaller filters on those images.
Okay.
Those are very good questions. So these are sort of the three filters that we're thinking about right now. And let's see how this thing actually works. So let's say we take the filter on the left, which is a right diagonal going down. So that is something that, let's say, we have created. And now we put it, we sort of imagine it being superimposed where this green square is. And when we have it superimposed, then what we do is we sort of, so now we're trying to sort of figure out the math behind it. So now we multiply each pixel value of the filter with each pixel value on the image where we have kept it. So essentially what we're trying to see is we're trying to come up with a mathematical way that will say, okay, this filter matches, this feature matches this part of the image, or this feature doesn't match this part of the image. So that's, we're just trying to come up with a mathematical way of seeing where, what part of the images does this feature match. So we go to each pixel value in the feature. So in this case, we are looking at the extreme right and at the bottom. And on the green square, can you guys see these colors clearly? I forgot to share these notebooks with you. I should have done that. Is it visible, or should I send the notebooks?
Yeah, it's visible.
Okay, awesome. I'll, at the end of the session, I'll share the notebooks with everyone. If I forget, please yell at me and I'll just do that. So on the green square at the bottom right, we see the value is 1. And the filter on the top left, the bottom right value is also 1. So we multiply them, we add them, we get the value 1. Sorry, we just multiply them. So if we do this for each pixel value in the filter, which is on the left top, because in this particular case, it's an exact match, the output we get is on the right, which is each pixel gets the value 1. Does that make sense? If not, I'll repeat it once quickly. If it still doesn't, then please tell me and I'll go to it again. So for each pixel, let's say the top left of the filter, you multiply by the top left of the green square. These are both 1 into 1, so we'll get 1, and we'll put it on the right matrix in the top left position. So we'll do that same with all the 9 pixels in this case, and we'll put all the 9 values on the right. In this case, because we just have 1s and -1s and all of them had the exact same values, we have 1s in all the squares of the matrix.
Avneet, sorry for this. Can you go back and tell me how you created the filters?
So here we are creating by ourselves, by our own imagination, thinking about what are the basic shapes that define an X. In real world, if you train this using a deep neural network, then the deep neural network will come up with these filters by itself using optimization algorithms like gradient boosting, basically back propagation using gradients. So
Do
here
we tell them the size of these filters? Like the 3x3 was a choice that you made.
Correct. That was a choice that we made. The actual pixel value is something that the algorithm can learn by itself.
That's fine. But my question is, how did you decide the size? Or how do we tell CNN to figure out the size?
So the size is something that you'll define.
Okay.
And so in your case, let's say you're looking at faces. And the key characteristics there are eyes and nose and ears and mouth and chin. So then you would know by looking at these basic characteristics, what are the kinds of sizes of these objects that you're looking for within a face.
Mm-hmm.
So that would be for the layer that's a later layer. If you're looking for earlier layers where you're just looking for lines and curves and some dark straight lines or dark tilted lines, then those will be different sizes of filters. So those are the things that as a human, as a subject matter expert of those images and being aware of the size of those images, something that you'll figure out.
Okay.
So I hope this part makes sense. Now this is showing just the same thing. So we took the filter on the left top, we multiplied with all the pixels in the square, the green square, we got 9 ones. Then we just add them up and divide by the total number of pixels. So we get, in this case, 1. And then we put that at the center of where the filter was. So a 1 would basically mean that this filter was a very good match. And now we see the same idea that we use the same filter and we move it to the center of the image. And so you can see the green square at the center of the image. And we do the exact same thing. So we go to the top left of the filter, which is a 1. We go to the top left of the green square in the image, which is also a 1. We multiply them, we get a 1. We do that for 9 pixels here. So in 2 of the cases, which is the bottom left and the top right. So can you see in the filter, the bottom left is -1, and in the green square, the bottom left is 1. So we multiply that, we get a -1 in the matrix that we see at the top middle. So we get 2 -1s in here. So now we add them up, we divide by the number of pixels, we get 0.55. So we saw how we used the filter at 2 points. At one point it was an exact match, we got a 1. At another point it was a rough match and we got a 0.55. So this simple idea, you can see, is doing a reasonable job of checking whether the filter matches the image at that position or not. Does that sound okay?
Okay.
Awesome. So now what we do is we essentially take our filter and we run it through the entire matrix of the image. So we put it at the top left and it looks at the top 3 columns and 3 rows, and we get a number, and then we move it one step to the right. So it looks at column 2, 3 and 4 and the top 3 rows, and we get a number. Then we look at column 3, 4 and 5 and the top 3 rows, we get a number. So we move this until it reaches the end. Then we go one layer down. So we go from row number 2, 3 and 4 and columns 1, 2 and 3. And then after that, we do row 2, 3 and 4, columns 2, 3 and 4. So that's whole process of taking the filter and moving it across the image and doing the math to see, is this a good match for this part of the image? And then putting that number down. This process is called convolution. Any questions on that?
No.
Okay, awesome. So when we do this convolution where we take the filter and we go throughout the image and we take each 3 by 3 matrix and we get the similarity score and we put it in a square, what we get on the right is essentially a matrix with all these scores, and you can see that the diagonal values are sort of high because that's where this feature had done a decent job of fitting the image. So this is the output of the convolution of one filter with this image. So similarly, what you would do is you have 3 different filters and you run them through the image, and you get 3 outputs that you see on the right. So in the top one, as you might notice, the right diagonal values are the maximum because that's where the diagonal filter fits the best. If you look at the bottom, then the left diagonal values are the highest. because that's where this filter fits best. And if you look at the middle image, it's the one space in the exact middle that has the highest value, because that's where that filter fit the best. So essentially, what the CNN is doing, it's trying to figure out areas of image where these filters exist. And we'll have next time, I will have the next steps of this, where we'll see how these information can then be run through a dense layer, where each pixel that you see on the right hand side, the weight that's coming out, that becomes a bit of a vote that says, oh, I got this feature existing. So all those votes will then be given weights, and they can be passed through multiple dense layers. So then you can look at combinations of these filters. So the model will say, okay, I know this filter exists. And the next layer will say, I know that the first exists and the third exists. And it's important for me that both exist. So it'll look at those kind of combinations, and that will be used for the final prediction. So next time I will have some more slides on this, continuing from this idea, how the matrices that we're getting right now, where certain pixels have very high values indicating the presence of certain features, how those values then translate into votes, into saying, okay, these features exist in this image, so this may be a dog or this may be a cat. So does that, but this is the general idea of how convolution happens in images. And as Sendhil had mentioned earlier, so these patterns, whether we should learn a right diagonal or the filter should be a left diagonal, or it should be a cross, an X, these are the things that the optimization algorithm inside the deep learning neural network will learn on its own. So does this part of how convolution happens in images and how that finds small features in the overall images, does that make sense?
Yes.
Any questions around it?
No.
Awesome. Okay. So this is sort of the key essence behind convolutional neural networks. And CNNs are used in lots of places. If you want to figure out images of people, it's used in autonomous driving. You can use it in other places. So if you have a matrix, if you can represent your data in matrix, where the location next to each other is important, there you can use a CNN. So in case of sound, let's say each column is one timestamp. So each column is 1 second, second second, third second, fourth second. So you have seconds. And in the rows, you have different bandwidths for the sounds. So there's some sort of a connection. If one pixel of that has a connection with another pixel which is close to it. So as long as that condition is met, that there's a relation between pixels, you can even take other kinds of problems like sounds and run them through CNNs and do the same kind of things like categorization and stuff like that. So that's sort of the whole beauty of CNNs. And next time we'll go into how the votes that came out of these filters can later be used to make decisions about whether a category is a dog or a cat, a male or a female, and so on. So that's all for the CNNs. And if you guys are ready, then we will then turn to cross entropy. So are you guys okay with cross entropy?
Yeah. Go ahead.
Awesome. So this is more of a theoretical aspect behind entropy. It's behind it. It's about information theory, and essentially, what we are trying to do is in machine learning, we will have a distribution that we call labels. So let's say you have 1,000 images, half are cats, half are dogs. So you have a distribution of ones and zeros in there, where 1 can mean dog and 0 can mean cat. Or you can have a distribution of prices for houses that they were sold at. So 200,000 to 25,000 and so on. So there's a distribution of labels. Then our model has a distribution of what its outcome is, the predictions. And we're trying to figure out how do we measure the distance between these two distributions. So that's what we're going to look at. And this work essentially came from an American mathematician. His name is Claude Shannon. And he'd written a paper which about information theory. So all of that comes from that. So in terms of understanding uncertainty and how do we reduce uncertainty by providing information, things today will get a little bit intricate. So even if you don't get every aspect of it, I will repeat a bunch of times the main gist of the ideas. As long as you get the gist of the idea, then you'll have a good intuition about what's going on inside the algorithms. So if you think of bits, so let's say you have two possible outcomes of a coin toss, then those are equally likely. So there's a 50% chance you'll have a head, and there's a 50% chance you'll have a tail. So there are two outcomes. At the moment you tell somebody what the outcome is, by either saying a 1 or a 0, you reduced the uncertainty by 2. And that was encoded in 1 bit. Similarly, if you have 4 possible outcomes that are all equally likely, so those, if you want to transmit somebody the outcome of any one of them, you can encode them as 0, 0, 0, 1, 1, 0, 1, 1. So 2 bits, and you're reducing the uncertainty by a factor of 4. Same thing for 8 outcomes. If you have 8 possible equally likely outcomes, then you can use combination of how many bits?
3.
Perfect. So you can use 3 bits. All of them will be distinct, and they can provide this information. That's the general idea behind bits. Each of them divides your uncertainty by 2. So this is a simple example. If there's an equal likelihood that you'll have a sunny day and an equal likelihood that you'll have a rainy day, and your weather company provides you information saying which one it is, the amount of information it is giving to you is 1 bit. Now, instead of giving you a 1 or a 0, it may send you a text saying rainy. So that's a lot more bits it is using to encode the message. But as far as you're concerned, the actual value that you got out of it was 1 bit. And here's the same idea. If you have 8 possible weather conditions, and all of them are equally likely, as Senthil mentioned, you can encode them in 3 bits. And the simple formula for that is there are 8 equally likely outcomes. So you take the log of that to the base 2. Now, what if the outcomes are not equally likely? So there is one event which is rain, which happens only 25% of the time. So you have an event which is very unlikely. So event which is very unlikely, the probability is very low. Knowing when it will happen, the uncertainty is very high. Let's say a cyclone comes once in 3 years. It's a very low probability. Let's say you're in Seattle and it rains every other day. The probability is 50%. So when the probability is very low, and then that event happens, then the uncertainty reduction is much higher. So essentially, if the probability of an event is low, like a hurricane happening is very unlikely and it just happens, then the uncertainty reduction is very high, or lottery happening. So the inverse of the probability is a measure of its uncertainty. Does that make sense?
Mhm.
Awesome. So it is something that happens every day, like sun comes out every day. The probability is 1. So in that case, the uncertainty is practically 0. So here the probability is 25%, or 0.25. and we take the inverse of that. So it's 1 by 1 by 4, and we take a log of that, we get 2. So that is sort of the uncertainty reduction when we say that it has rained. So that's the basic formula. Now, if we look at 75%, then it's going to be log of 1 by 3 by 4, and the answer for that is 0.41. So if 75% of the time it's sunny, then you already know, okay, there's a very high likelihood that it's sunny. So if you do get to know that it's sunny, the uncertainty reduction is very little. So that's 0.41. But the rainy thing happens much less frequently. It's more like 1 out of 4 times. If that happens, the uncertainty reduction is much higher. So that's log of 1 divided by its probability. So that's a higher number, that's 2. So in general, if we want to find out on average how much useful information is the weather system providing us, that essentially on average how many times is it sunny, so that's 75% of the time, so that's 0.75 multiplied by how much uncertainty reduction happens when we know that it's sunny, plus 25% of the time it'll be rainy, so that's when the weather system will tell us, okay, it's rainy. So when it does tell us, then the uncertainty reduction is 2. So we multiply that. So if we add these up, we get 0.81 bits. So that is essentially the formula for entropy. So it is measuring how much uncertainty is there in the system. Now, if we change this formula a little bit, if we say that half the time it's sunny and half the time it's rainy, then what is the entropy? 75? Correct. Absolutely brilliant. So the uncertainty will increase because now we have an equal chance of sunny and rainy. And essentially we'll have 0.5 multiplied by 1 plus 0.5 multiplied by 1, and we'll get 1. So is this sort of intuitively clear that entropy is trying to measure the uncertainty?
Yeah.
Awesome.
So by definition, it's a minus, huh?
Yeah, that's because you get essentially when you calculate, so here it's 1 by 1 by 4. So the probability was 1 by 4, and we'll take it the inverse of the probability. So that's 1 by 1 by 4. If you inverse that, you get a 4 here by putting a negative sign.
Where do you put it? If it's a negative sign, means what? It's in reciprocal. So the entropy here is 2, minus 2. Is that what it's saying?
For this one, so it's 1 by the probability. So that's 0.25.
Yeah.
Now, if we inverse that, so
I think entropy by definition will be negative.
yeah, by definition, it is a negative.
Okay, go on, update. Don't worry about this one. So
Okay.
it's a measure of uncertainty which we want to minimize. Is that what it is? Maximize.
I'll quickly come to that. So related to entropy is cross entropy, and we'll come to that. And it's the cross entropy that we want to minimize. So if we look at this case, so as you had mentioned, if we have 8 possible outcomes, then we can measure that by the 3 different bits. So essentially that's log of 8. If we take a negative sign on that, that becomes log of 1 by 8, which is the probability. So that's why it's a negative log of probability. So log of 8 was giving us 3, which is what we want, which is the same as negative of log of 1 by 8, where 1 by 8 is a probability of any of these 8 events. So that's how a minus log of the probability is what we have in the formula. Thanks for that question. So in this case, it's sort of fairly simple that if there are 8 equally likely events, then anytime we provide somebody the information, the weather station tells us which event, they reduce our uncertainty by 8 times. So that's the useful information, is negative log of the probability. So that's 3 bits. And we're also using 3 bits to encode. So that's perfect. Now, so in this case, the message length is the cross entropy. So entropy means how much useful information did you get? Cross entropy is how much information was sent to you. So the message length, which in this case is 3 bits, is the cross entropy. And this particular case, the information that you got was also 3 bits. So the cross entropy and the entropy were the same. Now we look at this case where you have 8 possible weather outcomes, but the first 2 are much more likely. So if we still use the same formula, because the first 2 are much more likely, our overall entropy is 2.23 bits, because so the entropy has reduced. What does that mean? It means that the uncertainty has reduced. Now, why has the uncertainty reduced? Because the first 2 kinds of weather outcomes are much more likely. So previously they were all equally likely, so there was very high uncertainty, but now it seems like there's a weather pattern that the first 2 are much more likely, 70% of the time. So the uncertainty has decreased, hence the entropy has also decreased, but we are still transmitting the information with 3 bits. So the cross entropy has remained 3. So here we had 3. Here also we're using 3 bits, but the uncertainty has decreased, so the entropy has decreased, but the cross entropy is still the same, which is 3. The difference between the cross entropy and the entropy, that is what we're trying to minimize. And the next image and the one after that will sort of show how or why. So if we see that 35% of the time the first 2 events are happening, so 70% of the time those are the 2 events that happen. So then we can encode them with fewer bits. And the events that happen rarely, those we can encode with more bits. So if we change the way we formulate the information, then the overall bits used on average that are sent by the weather system, that reduces to 2.42. So this is the cross entropy, 2.42, and it's much closer to the entropy, which is 2.23. So that is essentially what we're trying to do. So if we have a decent understanding of the underlying distribution, then we can code our system in such a way that it is closer to the original system. So in this case, we had an understanding that the first 2 events are much more likely. So those are the events which we gave the smallest amount of bits to code. Now what if we do the reverse? What if the weather is completely opposite? We keep the same coding. So the 35% likelihood are super rainy, and we have the maximum number of bits, 5 bits. So the overall cross entropy increases to 4.58. So here we are not using the knowledge of the original distribution, which said that the last 2 events happen the most. Ideally, we should have had the minimum bits used for them, so that we are using minimum bits sent over the information system. So if we have a good understanding of the underlying system, like we had in the first case, then the events that were happening most often, we would have given them the smallest number of bits. And the events that are happening most rare, you would have given them the biggest number of bits. So essentially, if we, like we saw in the first case, in this case, where all of them were equally likely, and we had that knowledge, in that case, the entropy and the cross entropy were the same, which was 3. In the second case, there was a bigger difference. The cross entropy was 3, but the entropy was 2.23. Then we used the knowledge that the first 2 events are very likely, and we made the message length smaller to 2 bits for the first 2 events which were very likely. That reduced the cross entropy to 2.42. So if we have a good understanding of what the true distribution of the data is, then the difference between the cross entropy and the entropy will be the least. That's sort of the key idea. That entropy is sort of measuring the overall uncertainty. That's the information that you provide when you reduce that uncertainty. Cross entropy is the way to provide that information, and if you have a very good understanding of the distribution of the data underneath, then your cross entropy and entropy will pretty much be the same. So that's essentially the formula for cross entropy, similar to entropy, except instead of P log P summation, it's P log Q, where Q is the distribution that we have assumed and P is the original distribution. So if this was a categorical distribution, then let's say P was the probability that is a dog, that would be 1, and the prediction Q was 0.9, then we would have P multiplied by log of 0.9 plus, then we would have another one, which is the probability of a cat would be 1 minus the probability of a dog. So that'd be 1 minus P log of 1 minus Q for the dog. So that's the formula that's essentially used in cross entropy. And the difference between entropy and cross entropy is called KL divergence. So this is a metric that if you read machine learning papers, you'll come across many times. And essentially, the difference between the entropy and the cross entropy is KL divergence. So in machine learning, when we say we want to reduce cross entropy, what we're really saying is we want to make cross entropy smaller and make it as close to the actual entropy. So essentially, we're trying to minimize that difference, and the difference is called KL divergence. So that is sort of the general idea behind what cross entropy is. So entropy is a measure of uncertainty, or how much uncertainty is reduced when you provide that information. Cross entropy is how much bits you're sending. And if you have good amount of information of the underlying distribution, then you can squeeze the cross entropy to be as close to entropy. And that difference is called KL divergence. So what your algorithm is essentially trying to do is it's trying to reduce the cross entropy and make it as close to the entropy as possible. So if we take a simple example here, so in this case, we have a categorical variable. In this case, this is called a one-hot vector, which means all the other categories are 0 and one of them is 1, because this is a red panda. So that is sort of our real distribution. So the probability of, in the true distribution, the probability of being a cat is 0, probability of being a dog is 0, and so on. The probability of being a red panda is 1. And our predicted distribution gives different probabilities for different animals. So if we use these two probabilities where P is the actual and Q is the predicted, so for everything else, P is 0, only for red panda it's 1. So it'll be 1 and then log of 0.25. So that would be the cross entropy And if we are able to make this probability 1, then we can essentially drive the cross entropy to be 0.
You mean the DL?
The KL divergence.
Level
In this, that will become 0. In this case, the cross entropy should also become 0. So log of 1 is 0. So if Q becomes 1, so we have 100% probability that's a real panda, then log of 1 will become 0. So that multiplied by 1 is 0. So this is a special case. So in general, yes, as you said, we want the KL divergence to become 0. This is a special case of one-hot encoding where in this special case, even the cross entropy will become 0. But yeah, as you mentioned, in general, we're trying to drive KL divergence to 0. So this is the general.
By definition, the original one will always be 0, no? With the one hot code vector.
Correct.
So if you're using one hot encoded vectors, the point would be to reduce cross entropy loss to 0.
Correct. Absolutely correct.
But in general, we don't need to have one hot encoded vectors.
We don't.
In which case, we do KL, minimize KL to 0.
Correct. Correct.
Okay.
Awesome. So yeah, these are the two ideas that I wanted to share today. Are there any questions around these? Okay, seems like we are good. So today we went slightly more theoretical, and I wanted to get a sense of any feedback on that. In the previous times, it was mainly on the code. So was it useful to sort of deep dive into the theory side? Should we have a combination of both code and theory? Should we have mainly code and a little bit of theory? Or should we have even more theory and less code? Do you guys have feedback on that?
Theory and code will help.
Okay.
It will take some time to understand the theory.
Right. So was today okay? Was it too much? Was it too little?
It was okay, but it still takes some time to understand all this.
Absolutely, definitely.
Yeah, she's right. It's theory is good, and but that mathematical part we need to understand more. So since we have a lesser background on that.
So you by mathematical part, you mean the formulas?
Yes, then that I'll have to go through again my +2 books and all because we forgot this thing, probability and a kind of thing.
Sounds
So
good.
so the rest thing is okay. The understanding and the theory is good. The coding I can do, but this formula I have to go through once because for me it's like how this calculating is again it's challenge for me to understand. But yes, I'll go through it and get back to you guys.
So the formula, so in the real world, if you are interviewing as a data scientist
Mm-hmm.
in some of the top tech companies,
Mm-hmm.
then they may ask you,
Okay.
like if you interview for Google as a machine learning engineer or data scientist,
Mm-hmm.
they pretty much ask you to write your own code to do the optimization. In that case, you will need to know. Most of the time, even in the interviews, they'll ask you your favorite algorithm. As long
Okay.
as you just remember the formula for your favorite algorithm, you're
Mm-hmm.
good. So
Okay.
even in interviews, you can, as long as you know one mathematical formula of your favorite algorithms, you can forget the others. The key thing is, as long as you get the basic intuition of what's going on,
Okay.
that's all you need. In terms of
Okay.
actually building these algorithms. If you're changing loss functions, then you'll have some idea of what each loss function. As long as you have that intuition, you're good to go.
Okay, great. Okay, thank you.
Awesome. Thanks a lot, guys, and hope you have a lovely Sunday.
Thank you.
Thanks.
Thank you. Thanks a lot.
Thank you.